Unlocking limitless energy, building a ZPE harvesting system. Hey everyone, today we're diving into the world of cutting-edge energy tech. We're talking about a Nyrrite-based zero-point energy harvesting system. Now you might be thinking zero-point energy sounds like something straight out of a sci-fi movie. And you wouldn't be wrong. This technology pushes the boundaries of what we thought was possible, potentially revolutionizing how we power our world. Buckle up, it's going to be a wild ride. From the Earth extracting ultra-pure dysprosium. All right, before we can bend the laws of physics, we need to start with the right stuff. And for our ZPE system, that means getting our hands dirty with some seriously pure dysprosium. We're talking 99.99% pure, people. This rare earth element is like the VIP ingredient in our recipe for nyrite. Now, purifying dysprosium is no walk in the park. We're talking about some next-level refining processes like solvent extraction or ion exchange. Imagine using giant magnets to carefully pluck out the exact atoms we need. It's basically atomic-scale surgery, and trust me, it's as cool as it sounds. Once we've got our hands on this ultra-pure dysprosium, we can finally move on to the really exciting stuff. Isotopic precision fine-tuning for quantum performance. So we've got our super pure dysprosium, but we're not done yet. It's time to get picky, like really picky, and separate out those specific isotopes we talked about. Think of it like this. You wouldn't bake a cake with just any old flour, right? You'd want the good stuff, the finely milled, perfectly sifted kind. That's what we're doing here with isotope separation. We're talking lasers, people. Laser isotope separation, to be exact. It's like something straight out of Star Wars, but instead of blowing stuff up, we're using these concentrated beams of light to carefully nudge apart our dysprosium atoms based on their tiny weight differences. It's mind-blowingly precise. The goal is to hit that sweet spot, 85% Di-164, 15% Di-162, and just a sprinkle of Di-161. This exact ratio is what gives nyrite its unique quantum properties, allowing it to interact with the zero-point energy field. Forging nyrite alloy synthesis in a high-vacuum inferno. All right, it's time to crank up the heat and create some nyrite. Picture this, a glowing hot furnace, temperatures soaring past 1,800 degrees Celsius. That's where our isotopically enriched dysprosium goes for a little meet and greet with some other special ingredients like titanium or tantalum. These metals act like the glue that holds everything together, giving nyrite its incredible strength and stability. But here's the catch. We can't let any oxygen crash the party. Oxygen at these temperatures is like a bull in a china shop, messing up our perfect blend. That's where the high vacuum furnace comes in. It sucks out all the air, creating a pristine environment for our metals to melt and mingle without any unwanted interference. We've got our nyrite ingots, but they're kind of like rough diamonds, full of potential but needing a little polishing to really shine. That's where directional solidification comes in. It's all about controlling how the nyrite cools and crystallizes, ensuring those precious isotopes are perfectly aligned. Imagine a line of dancers, all moving in perfect sync. That's what we want our nyrite atoms to do. Directional solidification helps us achieve this by slowly cooling the ingots from one end, encouraging the atoms to line up in a specific direction. This process not only strengthens the nyrite, but also enhances its quantum properties. The result? Beautifully aligned nyrite blocks, ready to be transformed into the heart of our ZPE system. All right, time to unleash our inner artists. We're taking those pristine nyrite blocks and carving them with intricate fractal patterns. Now, these aren't just any random doodles. We're talking about precise nanoscale designs that are crucial for interacting with the zero-point energy field. Imagine drawing on a grain of rice, but instead of a pen, you're using a beam of electrons or ions. That's the level of precision we're talking about. We're using techniques like electron beam lithography or focused ion beam etching to carefully carve these fractal patterns onto the surface of our nyrite plates. These patterns act like tiny antennas, amplifying the nyrite's ability to tap into the quantum realm. After all that etching and carving, our nyrite plates are feeling a little stressed, and let's be honest, who wouldn't be after all that nanoscale manipulation? It's time to give them a little spa treatment, cryogenic style. We're talking about slowly cooling these plates down to super low temperatures, around minus 196 degrees Celsius. This cryogenic annealing process helps relieve any internal stresses that built up during the etching process. It's like giving our plates a deep tissue massage, helping them relax and settle into their new fractal-enhanced forms. This ensures they're ready to perform at their peak when it's time to harvest some zero-point energy. All right, time to give our Nyrrite plates a supersuit. We're talking about a thin, nearly invisible layer of graphene, the wonder material of the 21st century. Graphene is like a superhero in the material world. It's incredibly strong, conducts electricity better than copper, and is practically transparent. In our ZPE system, graphene plays a crucial role in channeling the harvested energy. We use a process called chemical vapor deposition to gently lay down a uniform layer of graphene onto our Nyrrite plates. It's like giving them a delicate spray tan, but instead of a bronze glow, they get a boost in conductivity. Our Nyrrite plates are almost ready for their close-up, but first they need a stage to shine on. That's where our modular frames come in. These lightweight frames, crafted from a super-strong titanium aluminum alloy, provide the structural support and precise alignment our ZPE system needs. We've designed these frames to be modular, meaning they can be easily assembled and expanded. It's like building with Legos. But instead of spaceships and castles, we're building the future of energy production. Time to bring it all together. We're carefully installing those fractal patterned Nyrrite plates into our modular frames. This is where things get incredibly precise. Remember those alignment guides we talked about? They're crucial here, ensuring each plate is perfectly positioned, maximizing our energy harvesting potential. We're talking about nanoscale precision, folks. Imagine trying to stack playing cards perfectly, but instead of cards, you're using microscopic plates that are thinner than a human hair. Thankfully, we've got some high-tech help. Precision robotic arms, guided by sophisticated software, delicately lift and place each plate into its designated slot. Energy conduits channeling the quantum flow. Our Nyrrite plates are in place, ready to tap into the zero-point energy field, but we need a way to channel that energy, to harness it and put it to good use. That's where our energy conduits come in. These aren't your average wires. We're talking about high-conductivity copper conduits, coated in that super-slick graphene we talked about earlier. They're like the superhighways of the energy world, designed to handle the massive influx of power our ZPE system can generate. We carefully weave these conduits throughout our modular frames, connecting each Nyrrite plate to a central energy hub. All right, things are about to get chilly. Harvesting zero-point energy generates a bit of heat, so we need to keep things cool. Literally, that's where our microchannel cooling system comes in. We're talking about tiny channels etched into our modular frames through which liquid nitrogen flows, keeping our Nyrrite plates at their optimal operating temperature. Liquid nitrogen, with its super low temperature, is the perfect coolant for the job, ensuring our ZPE system runs smoothly and efficiently. All right, it's showtime. We've assembled our Nyrrite-based ZPE harvesting system, and now it's time to fire it up and see what it can do. But before we unleash the full power of the quantum vacuum, we need to make sure everything's working as it should. That's where our trusty vacuum chamber comes in. This high-tech chamber allows us to simulate the conditions our ZPE system will encounter in the real world, but in a controlled environment. We're talking about a near-perfect vacuum, free of any pesky air molecules that might interfere with our delicate measurements. Inside the chamber, we run a battery of tests, checking energy harvesting efficiency, thermal stability, and vibration resilience. Our individual modules have passed the test with flying colors, proving they can tap into the zero-point energy field and harvest its boundless power. Now it's time for the grand finale, assembling these modules into a network, a symphony of quantum energy generation. Imagine a grid of these modules, all working in sync, their energy conduits feeding into a central hub, a reservoir of near-limitless power. We carefully connect each module, ensuring redundant wiring and cooling pathways for maximum efficiency and safety. The result? a clean, sustainable energy source that has the potential to revolutionize our world. And there you have it, the 13 essential steps to fabricate the Nyrrite-based ZPE harvesting system. You've gone from extracting raw materials to assembling a network capable of powering cities. Remember, this is just the beginning. As we continue to unlock the secrets of the quantum vacuum, who knows what incredible breakthroughs await us? Stay tuned for more in-depth guides on cutting-edge technologies.